Hello, my dear students. In last class, we discussed about equipotential surfaces and their properties, and some examples for the equipotential surfaces, and also the relation between the electric field and the potential. That is, E is equal to minus of delta V by delta L. Today, I am to discuss about the potential energy of a system of charges in absence of an external electric field, as well as in presence of external electric field. First, I want to discuss about the potential energy of a system of charges in absence of external electric field. When the charge is transferred from infinite to a particular distance, if there is no external electric field, then the work done by that charge is taken as zero. Let us take that is W1, which is equal to 0. Then another charge of Q2, which is bringing or shifted from infinite, infinite distance to a particular point, which is at a distance, let us take R, from the charge Q1, then that is equal to W is equal to Q into V. That means already you know the equation for V, that is the electric potential, that is 1 divided by 4 pi epsilon naught Q1 by R, that into another charge, that is Q2. So therefore the equation number 2, so this equation will indicates the potential energy of a system of charges between two charges in absence of external electric field. Just you have to remember this equation. This is very important relation. Suppose instead of two charges, if there are three charges, then the potential energy of system of three charges in absence of external field can be written as, again, so you have to use this equation, that is U is equal to 100 by 4 pi epsilon naught Q1 Q2 by R12. It is the distance between the charges Q1 and Q2, and Q1 Q3 by R13. That is the distance between Q1 and Q3, and Q2 and Q3 divided by R23. It is R23 is the distance between the charges Q2 and Q3. So this is the equation for potential energy of system of three charges in absence of external electric field. You have to remember this is in absence of external electric field. Suppose if there is an external field, then what happens with the potential energy of the system of charges? Let us take the single charge. When the charge is moving from infinite distance to a particular point in an external electric field, there is work has to be done. That work is stored as potential energy of the charge. Let us take, if you take q is a charge, small q, then this equation, that is equation number 2.27, that is this equation will indicates the potential energy of that charge, that is equal to q v into bracket r, it is a vector. So therefore, that is the potential, that is U is equal to Q into V. It is the potential energy of single charge in presence of external electric field. Suppose the system having two charges in presence of external electric field, then take another charge which is shifted from infinite distance to a particular point, then that work done is stored as a potential energy, that is Q2 into V. So this is the potential energy of a second charge in presence of external electric field, and this is the potential energy of the first charge in an external electric field. Then there is another potential energy between those two charges, that is 1 divided by 4 pi epsilon naught q1 q2 by the distance between them. So therefore, the total potential energy of a system of two charges in an external electric field is given by U is equal to Q1V plus Q2V plus Q1 Q2 by 4 pi epsilon naught R. So this is very important relation. They may ask about 2 to 3 marks questions on this potential energy of a system of charge in absence of electric field as well as in presence of external electric field. The next point, that is potential energy of a dipole in an electrical energy external field here. So let us take the dipole in an external field, then what happens to the potential energy? So place the potential electric dipole, that is plus q and minus q, plus q and this is minus q, and this is the direction of electric field. So in this direction, then because of the force between the applied electric field and with respect to dipole, the torque, it experiences some torque, that is tau is equal to P cross E, or it is also taken as a P into E sine of theta. Then this can be, the deflecting torque can be neutralized by the another external torque, so that is given here, that is tau external at equilibrium position. Then the work done by the external torque will be, that is W is equal to integration of theta naught to theta, that is tau external into d theta. So tau means the torque, that is Pe sine of theta d theta. By integrating sine theta means it becomes cos of theta. Then if you put the ratios, then finally you get W is equal to Pe into bracket cos of theta not minus of theta 1. So this work is stored as a potential energy of a system. If you consider theta 1 and theta 2 as a 90-degree and theta, then the final equation now becomes the potential energy of a dipole in an external electric field, U is equal to minus of Pe cos of theta or which is also equal to minus of P into E. So this is important relation for the potential energy of a dipole in an external electric field. Okay, today I'm going to stop here only.